28, a lot of people are going to stay there before heading on. Because if you head on, you're in FinFET land. And yes, there's some learnings that are attached to that. But the fact is, people are moving very rapidly. You can see it here. Not as rapidly as maybe the previous generations, but so did we not move as rapidly at 135 because of new materials. It took some delay to learn how to do it. But what I can tell you is the chips that you see there are astronomically complex and extremely powerful. Now, in order to do that, there's a very big food chain of design. So you want to design some IP, you have to design it, you have to, of course, manufacture it. Around the manufacturing, there's test, there's PCB, there's packaging, there's TCAD, three-dimensional simulation, before you build anything. But really, the food chain that is most complex here is the design to manufacture. Starting with synthesis or high-level synthesis, power optimization already there, tests, floor planning, the most complex one of all, the place and route system, amended by custom optimizations, timing and engineering change orders, physical verification, yield optimization, lithography. This is a food chain that today delivers on a correct chip maybe 10 to the minus 14th in errors. It's unbelievable how automated this is. It's also unbelievable how much this continues to evolve. So much so that when FinFET came about, suddenly the question is, well, can you do all this 10 times faster? And so to take a Synopsys example, we invested in this. And while this is not as big an investment as some of you having to make fab decisions, this has been a 5-year effort to design a new platform with an objective to do a place and route system that will be 5 times faster with half as many iterations, so 10x productivity, by looking at a completely new infrastructure, new engines, and so on. And last but not least, it is imperative to be able to simulate the hardware before you have it, because the software teams want to start and get moving on this. Well, in order to do that, you need to be able to simulate. And verification today is the biggest task from a design point of view, because it is not only verification, but it has many subcomponents, such as simulation, of course, analog mixed signal simulation, a variety of verification IP blocks that are all helping in short circuit these things. Planning, the debugging is a big set of tasks. Static techniques are used to catch things up front. Formal techniques, and then coverage metrics, and a variety of accelerations, emulation, or FPGA-based design. All of these engines are now fully utilized to design advanced chips. And if we look at what needs to happen here, is we're dealing with the following challenge. If you look at this curve, what you see is the number of bugs found per week or per day over a period of time. And of course, at the beginning you design, you don't find many. Then you start to find a lot, deal with them, and then gradually it goes back down. And the question is, it never quite arrives at 0. And so you just hope that you have a long weekend where you find no bugs and then you ship it. But the fact is, it is a very big task, and you have not enough time to do it. And so this brought about the whole notion of shift left, which is, what can we do to accelerate this? And so we put a massive effort at looking at all the tools. Can you make simulation much faster? And the answer is continually yes. Analog mixed signal is faster. Can you automate debugging? Can you apply verification IP everywhere so that the designer doesn't have to do it? Can you use static and formal techniques? Is hardware emulation or FPGA useful? Can we move to a very different level of abstraction, such as virtual prototyping? And the answer is yes, 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 yes to all of those. But the challenge is, how can you make these things work together? And so here too, a 3.5, 4 years effort on our part has built a new platform with 3 key objectives. The first one is to have the fastest engines everywhere. The second one is to have a common compiler, meaning all these tools know how to understand the data the same way. The third one is to have a common debugging, so that we can actually look at the circuit from different levels of abstraction. And lastly, on top of that, we now have the capability to start automating some of those things by essentially having plug-in applications that the customers write themselves, we hope. But it's interesting to see the complexity and the growth of that. I always like to put things in perspective to biological systems. So you see bacteria, and you see a mouse, which has about 220 million DNA base pairs. So it's useful to compare to ourselves. You can see the human line, twice as high as the mouse, on a logarithmic scale, though. So we have a ways to go. Now, why am I showing this? I want to show off a little bit. Synopsys has 400 million lines of some of the most sophisticated code, and I'm very proud to say that we beat the mouse, at least that. Now, if anybody has ever tried to catch a mouse, the mouse is pretty smart. It's hard to do. So we're working on this, but why is that important? Well, because the many lessons that we've learned from such complexity, which is sooner or later an exponential will catch you.